In 1785, the French physicist Charles Augustin de Coulomb proposed a theorem which defines the force of attraction or force of different repulsion between two charged particles. Here we can see that two charged particles Q1 and Q2, they are of same charge, so there is a force of repulsion between these two charged particles. And down to that we can see that a two charged particle with different polarities, so there exists a force of attraction between these two charged particles. And this Coulomb's theory was essential to the development of theory of electromagnetics. So it is the tipping point of electromagnetism. The branch is evolved from the Coulomb's law. This law states that the magnitude of electrostatic force of attraction or repulsion between 2 point charges is directly proportional to the product of the magnitude of charges and inversely proportional to the square of distance between them. So in scalar form we can write it down as F, the force of attraction, is directly proportional to Q1 times Q2, which is upon the distance between the two charged particles. So the proportionality sign we can change with a constant Ke. Now the coordinates of Q1 is R1 and coordinate of Q2 is R2. The distance between Q1 and Q2 is R12, so which can be written in vector form as vector R1 minus vector R2. This is a scalar form of force of attraction or force of repulsion between two charged particles. If you want to express this force in vector form, then we need to multiply it with the unit vector which is acting along the force. I am taking a unit vector R12 cap. So R12 cap is R12, this vector R12, it represents the distance between the Q1 and Q2 in vector form, which is upon the absolute of R12. Now if you look at this R, it is also same as R12, so R can be written as modulus of R12. So by combining this, the unit vector R and the vector form of the force, we can write it down. The vector form of the force of attraction between the charged particle is F equal to Ke times Q1 Q2 R square times, this unit vector can be write down as R12. It is a distance between the charged particle, which is upon R12. Now we can replace this R square with R12. So R square become R12 all square. Now look at the denominator side. Here a modulus of R12 square and R12. So together we can write it now as R12 cube. This is the scalar form of the law and this is the vector form of the law, where K is the electrostatic force constant or electrostatic constant. Coulomb's constant is given by Ke 1 by 4 pi epsilon naught, where epsilon naught is permittivity of free space. of vacuum. Epsilon naught is the capability of an electric field to penetrate a vacuum. So by combining this constant, the force of attraction between two charged particles can be written as F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is a scalar form. The vector form of the Coulomb's law of force is 4 pi epsilon naught Q1 Q2. This is R12 Q. This is multiplied with R12 vector. So this is a scalar form. This is the vector form of the force of attraction. The value of Ke, electrostatic constant, 1 by 4 pi epsilon naught, is approximately equal to 9 times 10 power 9 Newton meter square per Coulomb square. So by using this formula, we can identify what is the force of attraction on a point charge due to n number of other charged particles distributed in the space. Let us consider a system consists of n point charges Q1, Q2, Qn at distance R1, R2 and Rn respectively. The force on nth charge is given by the vector sum of all the individual forces they are exerted due to the Q1, Q2 and other charges in the space, and this principle is called the principle of superposition. Let us take the force Fi on the ith charge can be written by Coulomb's law. F equal to sigma j equal to 1 to n Qi and Qj, which is upon 4 pi epsilon naught, the distance between them, that is r square. So here rji square, which is unit vector rji cap. So hence the force acting on a point charge due to a system of point charges is simply the vector addition of the individual forces acting along on that point charges due to each one of the charges. Since the force is a vector quantity, so let us represent this as a vector. So that's coming to the end of the today's session.